Look up at the stars, and all seems calm, serene, and unchanging. But look closer, and you can see that the night sky has been shaped by events of unimaginable ferocity.
Tonight, we're going in search of cosmic explosions.
We'll be taking a tour of some of the most violent events and showing how this explosive mayhem is changing our understanding of the universe.
Welcome to the Sky at Night.
We're here at the University of Leicester, where they're trying to track down the most powerful explosions in the universe.
We'll be exploring what these thankfully distant explosions are teaching us, as well as coming closer to home.
Coming up, solar physicist Lucy Green explores how explosions on the surface of the sun might solve one of the most enduring mysteries about our star.
What we'll see is a tube of plasma just erupting from the surface. That one right there.
We'll be joining the hunt for gamma ray bursts. Explosions on a staggering scale, whose light has taken billions of years to reach us, helping us to understand what was happening in the early days of the universe.
Plus, how explosions of particles in the Large Hadron Collider could help us finally discover what the universe is made of.
We've got all these theories and we need to shoot them down one by one and figure out what's really going on.
And Pete's here with his guide to the best way to capture this month's celestial firework display, the Perseid meteor shower. We're starting on more familiar territory with the Sun. Our star is a hotbed of explosive activity, and the influence of these violent events is often visible here on Earth.
In the last few months, many of you have sent in pictures of the Aurora Borealis, the Northern Lights, a rare treat when seen in the UK. It's also evidence of the explosive events happening on the surface of the Sun. The spectacular light show was caused by this explosive solar flare and the coronal mass ejection on the 21st of June. As impressive as these explosions are, they also give us an understanding of the inner workings of the Sun. Lucy Green has been exploring a certain class of these explosions, which is on the verge of helping us understand one of the longest running mysteries about our star.
The Sun's corona is one of the most mysterious regions of our star. Only seen with the naked eye during a total eclipse, this faint envelope of gas surrounding the Sun has proved to be a constant source of surprise to scientists. One aspect in particular has become one of the most enduring mysteries in solar physics.
The corona is hot. Now that might not be so surprising to hear. The trouble is, it's too hot. The atmosphere is a blistering 1 million degrees hotter than the surface.
It's a puzzle because the source of heat in the Sun is with thermonuclear reactions in its core. As you move further away from that central furnace, the temperature should go down. Just as the further away you sit from a fire, the cooler it is. But the corona breaks that rule.
The superheated corona really was a shocking discovery, and it's still a puzzle that we're grappling with today. Now, the only explanation is that the corona must be getting extra energy. The question is, from where?
There is a prime suspect. The Sun's magnetic field could provide the energy needed. The key is the way that the plasma, the electrically charged gas that makes up the Sun, interacts with the Sun's vast magnetic field. It's a complex process, but luckily we can see this relationship in action right here on the Earth.
Yes.
I've come to the Cullum Centre for Fusion Energy. Their goal is to recreate the nuclear fusion at the heart of our star. To do so, they built a reactor called MAST. Inside, they create plasma and a very strong magnetic field, as we have inside the Sun, but on a much smaller scale.
We're standing right at the bottom of where the plasma will sit. It'll be between 70 and 100 million degrees, and it'll be held almost like by elastic bands by magnetic field lines that curl around that plasma and hold it in place right here, right just up here.
And this touches upon something that's very intriguing and quite exotic about a magnetic field and a plasma or an electrically charged gas, that the magnetic field is able to exert a pressure and hold it in place.
Well, we always say that, the magnetic field is frozen to the plasma. It's the fact that it's stuck to the magnetic field that allows us to hold the pressure and the temperature to make nuclear fusion happen.
High-speed cameras capture MAST in action. You can see the faint ball of plasma, but not where the magnetic field is, until with a flash, part of the plasma manages to break out.
Occasionally, there's too much pressure inside the plasma, and what we'll see is a tube of plasma just erupting from the surface, tied to a magnetic field line, like that one right there.
Yep.
Right? What you can see is big stripes across the screen. Those stripes are magnetic field lines.
Which are invisible, but we can see them because the plasma is frozen into them and it traces out the structure. Absolutely magnificent to see. The same process happens in the Sun, where the plasma is bound into the Sun's magnetic field. But there is one additional factor that may help explain why the corona is so hot. Imagine this black ball represents plasma inside the Sun. And imagine that this elastic band is one of those magnetic field lines threading through the plasma. Now, the plasma near the Sun's equator spins much more quickly than it does at higher latitudes. And because the plasma and the magnetic field are frozen together, that means the magnetic field at the equator gets pulled out over time and actually ends up getting wrapped around the Sun. The magnetic field amplifies and it starts to get twisted, and this generates energy that's stored inside that magnetic field. And eventually that magnetic field rises up through the Sun, it bursts through the surface into the atmosphere, carrying with it colossal amounts of energy. In fact, enough to power the most energetic explosions in the entire solar system. We know them as solar flares. Sudden explosions of light across the spectrum, each one equivalent to detonating millions of hydrogen bombs. And that ferocious release of energy heats the corona. It seems like the perfect combination to finally solve the mystery. The twisted magnetic fields provide the energy, and it's released into the corona during a solar flare. But there's a problem. Flares, as large and powerful as they are not frequent enough to keep the plasma of the corona heated constantly to its million-degree temperature. Yet flares could still be the answer. I've come to meet Philippa Browning, who models nanoflares, very similar to the big solar flares I study, only 1 billion times less energetic. But although they're small, it's thought they're happening all the time. Your work looking at solar flares involves running simulations like this, creating simulations like this. What is it that we're looking at?
We're simulating here a smaller flare, and what we're doing is we're taking the magnetic field lines and we're just twisting them. What that means is we're actually building up energy in the magnetic field. And as they become twisted too far, the whole thing kind of becomes unstable. We get magnetic field lines which are misaligned, which break, reconnect, and then this magnetic energy is released. That heats the plasma.
So from the simulations, you can get a measure of how much energy is released. during these events. Are you able to say whether there's enough energy?
We can actually calculate the temperature of the plasma, and we are getting plasma heated to temperatures of 1 million degrees and even more in some places. But what we still need to know is whether these events are frequent enough to actually keep the corona hot. But of course, because they're so small, you can't see a nanoflare individually in the way that you can see a large flare.
Philippa's simulations can tell us what to look for. The nanoflares should give out a faint signal in X-rays. The trouble is that in normal conditions, that signal is drowned out in the glare of the sun's activity. But in the next few years, the sun will move into a period of lower activity, a solar minimum. When that happens, the plan is to point a satellite called NuSTAR at the sun. NuSTAR has a very sensitive X-ray detector, and with the sun in its quiet period, it might just be able to detect the emissions given off by the nanoflares.
If NuSTAR does detect that faint X-ray glow coming from nanoflares and crucially tells us how common they are, it will be a huge step forward in finally solving the long-standing mystery of why the sun has a corona that is so hot.
Now, from the largest explosions in the solar system to the most energetic explosions anywhere in the universe, gamma-ray bursts. And Maggie's been catching up with Dick Willingale to find out what these explosive monsters can tell us about the cosmos.
Dick, let's start with the fundamentals. What is a gamma-ray burst?
Well, gamma-ray burst is a very short burst of gamma radiation, which lasts from something like a second through to maybe tens of seconds. And we've actually worked out that they are all extragalactic.
Ah, so none within our galaxy?
None are within our galaxy.
So I've heard gamma-ray bursts described as the most powerful explosion in the universe. Is this truly the case?
They are indeed. They put out more energy in a few seconds in gamma rays than the sun puts out in its entire lifetime.
But that's the whole lifetime of the sun, and that's a lot of power.
That's a lot of power, yes. But we see all that coming out from a gamma-ray burst in a few seconds.
So if that's the case, should we be worried? I mean, if it happened locally, what would we...
If it happened locally, we'd be in trouble. But we shouldn't be worried because actually the chance of that happening is very, very low.
Yes.
In fact, it's probably never happened in our galaxy.
OK, so massive devastation if it happened, but the probability is incredibly small.
Absolutely, yes, yes.
And so I guess we can detect them in other galaxies because they're just so very bright.
Absolutely, yeah. The reason that we can detect them at all is because they are so powerful. In fact, we can actually detect them right to the edge of the universe.
Oh, wow. So now, when these bursts go off, what do we think is the mechanism behind them? Why do we get gamma rays?
Well, there's two candidates. One is that they're the collision between two compact objects, probably two neutron stars, and that collision is responsible for the short burst. The other is the collapse of a massive star, say 30 times more massive than our sun. That star basically collapses at the end of its life, forms a supernova, but also, by some magic, also produces this very, very intense burst of gamma radiation.
These are hugely powerful events. What can they tell us? Can they give us other information?
They can indeed, yes. So every time we see a gamma ray burst in the sky, that tells us in that direction, at that point in the sky, a star has died. But they're so far away that that star was basically existing very, very long time ago. So if we study them very carefully and we can understand enough about the gamma ray bursts, we should in principle be able to work out something about these stars that were actually going bang very, very early on in the universe.
Yes,
in fact, actually, we can potentially see remnants of the first stars that ever existed in the universe.
Oh, wow. OK, so getting that insight, this is amazing.
This is the only way we can do it.
Well, I look forward to hearing more. Thank you very much, Dick.
Thank you.
Although they're very bright at first, gamma-ray bursts often fade away within moments. And so the biggest challenge is to point a telescope at them before they vanish. As gamma rays can't penetrate the Earth's atmosphere, the only way to see a gamma-ray burst directly is to put a telescope in space. The SWIFT spacecraft is designed to spot when a burst happens and immediately swing round to focus its telescopes on that particular point in space. I've been talking to Kim Page to find out more.
This is a quarter-scale model of Swift.
Okay.
And it has 3 telescopes on board. This funny-shaped one is the BAT. That's the Burst Alert Telescope, and that's the gamma-ray detecting instrument. And then we have these 2. This is the X-ray telescope, the XRT, and around here, the UV-OT, the UV optical telescope. So the BAT can see about 1/6 of the sky at any one time. So it detects an increase in gamma rays and works out that, yes, it is a new source. It's not something that we've seen before. And it will send the commands to the spacecraft to slew round to point these 2 in the right direction because they have a much narrower field of view. It usually takes between about 1 and 2 minutes to get into position, which is where the name Swift came from.
So it's important to get there very quickly.
Absolutely, yeah. Without the information in the first couple of 100 seconds, we would miss out so much of the science.
So while all of this is going on, when do you lot find out about it?
So when the BAT detects a new gamma ray burst, we get text alerts to our mobile phone. So we usually know within seconds that there has been a new gamma ray burst. We get on the telecom, we discuss it. It's been automated enough that not a huge number of people actually have to dial into the telecom anymore, and it is noticeable that overnight people don't tend to. I do, because I'm nosy. If we're on call, any burst that goes off, I will dial into the telecom. It's just the thrill of knowing that I'm one of the first people to have seen these data. It's just really exciting.
So you were on duty earlier this week.
We were, yes. So the duty roster switches between the US, the UK and Italy, specifically for the X-ray telescope side of things. And yeah, we were on duty. We actually had 3 bursts go off during our duty week, which was pretty cool.
So how often do these things happen?
We believe that gamma ray bursts go off in the universe probably about once a day, but Swift doesn't detect all of those. So on average, Swift detects about 90 bursts a year. Just under 2 a week on average, but we've had 5 in a 24-hour period before, and that was fun.
But that number's extraordinary, 90 a year.
Yeah.
And you think it's 1 a day in the universe. So we're capturing 1/4 of all the gamma ray bursts that happen in the universe.
Swift is, yes. Before Swift, there weren't any telescopes that could do this on their own without human intervention, so it would be hours before they could follow up. Swift has completely revolutionised the field of gamma ray bursts in the 10.5, almost 11 years since it was launched.
So how many have you found in those 11 years?
As of today, 977.
OK, well, we need the 1,000th one to be exciting.
Yes, we're counting down to that. We reckon it should be 1,000 before the end of this year.
Well, here's to number 1,000. Good luck.
Thank you.
Coming up, how explosions of particles from collisions in the Large Hadron Collider could help reveal what the universe is actually made of. But first, here's Pete with details of the spectacular cosmic firework display visible in our own atmosphere this month.
The Earth is currently ploughing through the debris trail of comet 109P Swift-Tuttle. Now, as we encounter the dust particles strewn around the orbit of the comet, so that results in a spectacular celestial firework display, and that's what we know as the annual Perseid meteor shower.
As the cometary particles collide with our atmosphere, it makes for a beautiful spectacle. To get the best view, you need a spot like this with a nice wide open view of the sky and as little light pollution as possible.
Now, probably one of the most important bits of kit which I like to bring with me is going to be something like this, which is a sun lounger. Now, what you'd need to do is look up in the sky at an altitude of about 60 degrees or so, and you can look anywhere around the sky. A meteor could occur in any particular direction. But early evening, I like to look towards the south, where you've got a lovely view of the Milky Way coming down. And as you go past midnight into the bit before dawn, then I turn around and look towards the east and the southeast.
This year, the shower should peak in the early hours of the 13th of August, where you could see as many as 20 to 50 meteors an hour, depending on how clear your sky is. Although that sounds like plenty, they can happen quite sporadically, so plan to observe in 30-minute chunks at least.
And that is why I've got the sunbed with me, because the sunbed means I can watch for meteors and I can be really comfy outside.
This is also one celestial event that is relatively easy to photograph. It's best to use a DSLR camera set to manual mode. Use something like a 28 to 50mm lens set to manual focus and pre-focus it to infinity. Open the aperture as wide as it will go and set your ISO to 1600 or higher.
And I would typically use an exposure of about 30 seconds or so in length. Now, if you set the camera to continuous shooting mode, then if you hold the shutter button down, it'll continually take 30-second exposures for you. Now, it's a bit tedious to stay with your camera and keep the shutter button held down, so use a remote release cable. Now, with one of these, you can press the button down and lock it open, so the camera just continually takes shots for as long as the battery lasts. So it's a bit like celestial fishing, trying to photograph meteors. You can sit back on your sunbed, enjoy the view and let the camera do all the work, and hopefully you'll get a good bite.
If you do capture a meteor, the photo may reveal something that's easy to miss with the naked eye. Its beautiful colours. These colours are a result of what's happening to the often tiny particles of comet as they pass through the atmosphere, as I can demonstrate.
Now, what I've got here is a sealed tube of air with a plunger, and if I push the plunger down, it compresses the air and the air heats up.
You can see the effect on this thermal camera, the warm orange of the tube against the blue of the cool grass.
And exactly the same thing is happening with a Perseid particle as it's passing through the atmosphere at the incredible speed of 58 kilometers per second, which is really pretty fast.
The air in front of the particle is compressed, and that causes its temperature to rise dramatically.
And when it reaches a temperature of around about 1700 centigrade, it gets hot enough to vaporize material off the front face of these particles. The cloud of material which is released interacts with the superheated atmosphere, and the net result is that light is given out. So that's what causes this streak of light across the night sky, which we know as a shooting star.
The colours come from atoms within the atmosphere and vaporized meteor material, taking in the heat energy and then re-releasing it as light. Oxygen tends to give out green light, while molecules of nitrogen give out pink light.
The Perseids are a spectacular reminder of our dynamic solar system, and to be honest, they're one of my favourite sights throughout the entire year. And the beauty of them is that all you have to do to see them is to lie back and enjoy the show.
For the rest of this month's night sky treats, and for more tips on getting the most from the Perseid meteor shower, head to the Sky at Night website for the rest of my August night sky guide.
Now, to an entirely different type of violent event, the highest energy collisions we've ever created. The Large Hadron Collider is the world's most powerful particle accelerator. Within its 27-kilometre ring, subatomic particles are smashed together at close to the speed of light, creating explosions of new particles that have helped push back the boundaries of our understanding of the universe. Now, after a 2-year upgrade, which has increased the energy of these collisions, the Large Hadron Collider might be on the verge of answering one of the most fundamental questions. What exactly is dark matter? Finding the answer is crucial. Gravity sculpts the large-scale structure of the cosmos, and the strength of that gravity depends on how much matter is present in the universe. Only there isn't enough normal matter to explain why the universe looks the way it does. There must be some other matter out there. We call it dark matter, and the race is on to detect and discover its true nature. To find out more, Chris has been speaking to Malcolm Fairburn.
It's a strange thing, this, looking for the stuff that makes up the universe in a hole in Switzerland. So how can the LHC help us with this dark matter problem?
Well, We know from astronomy that there's a great need for dark matter. Now, what the LHC might be able to produce dark matter. So what we do at the LHC is we accelerate particles very, very close to the speed of light, so they've got a huge motion energy, and then we smash them together, and you get this explosion of debris in all directions, because you're converting energy into mass, in particular the mass of new particles that you've never seen before. We've got lots of theories about what dark matter might be, but there's a big class of theories called WIMPs, or weakly interacting massive particles. And it turns out that this class of theories, they lie in the correct energy range, such that we've got a good chance of being able to create those particles at the LHC.
Okay, so it's a detective story. We're trying to understand what's created. How would you know that you'd created dark matter? What would you see? Okay, so the difficult thing is if you create a dark matter particle and it moves out, then it doesn't set off the detector. We can't build a box for detecting dark matter
particles.
No,
it just flies through everything. So what you need to do is you need to detect its presence indirectly. So if you think about two protons coming together down the beam pipe and colliding in the middle of the detector, they've only got momentum in that direction along that line. But then if they create an explosion in that direction, so you get particles moving off in that direction.
Heading out into the detectors.
Because you originally had no momentum in this perpendicular direction at all, you know that if you get some momentum in that direction, you have to have an equal and opposite amount in the other direction.
And so most of the time, we'll see a jet of particles going here and a jet of particles going here.
Yes, but if you see a jet of particles flying off in one direction and not in the other, then you know that something's flying off in that direction, but you just can't see it.
So you know you've missed something.
You know you've missed something.
So how do we go from seeing that there's missing energy to the properties of a dark matter particle?
So, for example, if you did create particles in this way, you might be able to find out how massive they are, how much they weigh, and how it interacts with other particles in the Standard Model, like protons, for example. But of course, that evidence alone will not be enough to convince us that we've seen the dark matter that's flying around in space.
Just give us a clue as to what to look for.
It would be a very exciting clue. Everybody would be very pleased.
Would that be, we all pack up and go home at that point? We know what dark matter is?
If you see something flying out of the LHC that you can't detect, you only know that it's stable for the very few nanoseconds it takes to leave the detector.
A few billionths of a second.
Exactly. But we know that the dark matter in space has been stable for 13.7 billion years.
Since the beginning of the universe.
Exactly. So it would be the beginning of, it would be an indication that maybe we've detected dark matter, and then we'd have to see it somewhere else as well to be absolutely sure.
So there are reasons to be cheerful. We might see something, but what if we take the pessimistic view? What happens if we don't find dark matter in the LHC? Does that tell us something?
Well, it doesn't mean that dark matter doesn't exist. That's important to understand, because there are other theories where dark matter is either a lot lighter and you can't detect it using the LHC, or a lot heavier. So it just rules out a class of theories, and of course that's what we have to do. We've got all these theories and we need to shoot them down one by one and figure out what's really going on.
I love the way that the small scale stuff, the particle physics, connects to the physics of the very large, to cosmology. And so what would you like to see coming out of the LHC in the next couple of years?
It would be great if we discovered dark matter, or something which could be dark matter. That would be fantastic. But I think if you ask most people what they would most like, it's something completely bizarre that we weren't expecting, something unexpected. That would be the most interesting thing.
It's an exciting time.
Yeah, very exciting.
Well, come back and tell us when you have some dark matter, or when you have something else.
I'd love to, yeah.
Thanks a lot. And that's it for tonight's programme.
Next month, we'll be looking at the dynamic nature of the night sky and showing how over periods of thousands, millions and billions of years, the constellations over our head change beyond recognition.
And don't forget to check out our website at bbc.co.uk/sky at night for more on what to see in the night sky, and plenty on everything we've talked about in tonight's show.
In the meantime, get outside and get looking up.
Good night.
And if you want to revisit historical planetary flybys, including Jupiter, Uranus, Saturn and Pluto, take a look at our collection of archived Sky at Night programmes, available now on BBC iPlayer.